Lengths, areas, and volumes is what we're still talking about. And since we've taken care of the beginning ideas like measurement and units, as well as perimeters and line segments, it's now time to start looking at different shapes and we get to consider lengths, areas, and volumes attached to them as much as possible. So, the video here is about making sense of triangles, making sense of triangles. Of course, I know triangles are some of the most common shapes we know about that we see in our day-to-day lives. But I mean, this video will help us to dissect the whole idea of triangle and everything you may need to know about triangles. So first of all, making sense of triangles, right? So first we start with triangle basics, talking about types and properties of triangles. And first thing we talk about introduction, and we get to, I mean, I think in the last video, I believe, or the in the first or second video, one of the two, I started talking about the whole idea of a zero-dimensional object, which is just a point. When you have two or more points, then you have a one-dimensional object, which is a line. And then when you put three or more lines together, if you put two lines together, you can hardly get anything. Maybe two lines can intersect, they can be parallel, and all of that. They can be inclined at an angle or something. But by the time you put three lines together, you have the first polygon, which is called a triangle. So a triangle is a polygon with three sides and three angles. I mean, that's what it is. So as the word implies, right, you have three angle triangle. You have a triangle, and as you can see, tri means three. Okay, so you have three angles in short. So when you have a triangle like this, you have one, two, th three sides, and then you have one, two, three angles. So a triangle has three sides and three angles, basically. Okay, so it's a polygon with three sides and three angles. So we usually name a triangle with capital letters at the vertices. So if you want to name a triangle, you say it's like triangle ABC. So we can have this now to be triangle A. Anyhow, your A can start from anywhere, but let's do ABC this way. So you have triangle ABC. So we use capital letters like that for triangles. Then triangle ABC has vertices ABC and sides AB, BC, and CA. So these are the vertices now. So this these points, this is vertex A, vertex B, vertex C, and we have sides AB, AC, and BC. Those are the three sides of the triangle, right? And then we have the angle at A is written as angle A, and the side opposite it is written as A. Okay, so the angle here, the angle here is written as, so this is like angle A, angle angle B, angle B, and angle C. And the side facing each angle is named in using small letters. So this side is facing angle A. So this is side small a. This side is facing this side is facing angle B. So this is side small b. And this side is facing angle C. This is side small c, like that. So basically, you have a triangle this way, A, B, C, and this is side A, B, C, like that. Okay. So um, having said that, of course, so similarly, you have angle A opposite side A, angle B opposite side B, and angle C opposite side C. Settled. Then we can talk about types of triangles. So what types of triangles are there? We have uh different types. We have scaling triangle, where all three sides are different. All three sides are different lengths, and all three angles are different. So let's talk about scaling. So imagine you have scaling triangle and all the three sides are the same. All the sides are the same. Oh, sorry. All the sides are different. One, two, three. The sides are different. Okay. And of course, the angles, one, two, three, are all different. That's a scaling triangle. all the sides are different, all the angles are different. All the sides are of different lengths, all the angles are of different sizes. Then we talk about isosceles triangle. So two sides are equal. The angles opposite the equal sides are also equal. Example, AB is AC, then angle B is equal to angle C. So look at this now. For a for an isosceles triangle, okay, you have this. So this side and this side are the same, and this side is different. Or any two of the sides can be the same. It doesn't have to be these two sides. It could be this and this. All right. So, but two of the sides are equal, and since two of the sides are equal, uh, the angles facing the two equal sides are also equal. So it means this angle facing this side with one stroke, is this angle with this, you know. So in the same way, this angle will also be the same. So this angle will be equal to this angle. And of course, this angle will be the only different one because it is facing the only different side, right? So, example, we have AB. If AB is equal to AC, imagine that this is AB. Okay, let's say this is ABC. So you see now that AB is equal to, okay, I think I want to do it this way. Okay, I think it's better to do it this way. A BC. Yeah. So here now, AB is equal to AC. Okay. Because AB is equal to AC, this AB is equal to AC. Automatically, angle B is equal to angle C. That's the deal we see in this situation. And that is why we say that the base angles of an isosceles triangle are equal. All right. So that information can actually help us to look for angle and to solve a triangle. So now we have the third one to be equilateral triangle. All three sides are equal. All three angles are equal. Each angle is 60 degrees, right? So you have for equilateral, all three sides are equal. So you have equilateral triangle. All three sides are the same. All the three angles are also the same. So if you have A, B, C now, okay? If you have A, B, C, so we say that angle A plus angle B plus angle C are all equal to 180 degrees because the sum of angles in a triangle, it will always add up to 180 degrees. But because these ones are, so we now know that angle A is equal to angle B, angle A is equal to angle B is equal to angle C. So that simply means that so since A plus B plus C is 180 degrees, so an angle A is equal to angle B is equal to angle C. That means that will simply be 180 degrees over 3, which is equal to 60 degrees. So each angle in an equilateral triangle is 60 degrees each. Okay. So, and then we have what you can call a right angle triangle. Before we even talk about a right angle triangle, I would rather like to see, so because these are the four types presented here, but for me, I like to categorize types of triangle according to sides and according to angles. Okay. So if I'm going to classify according to angles, so right angle is going to fall there. And the key thing about a right angle is that it has only one right angle, an angle of 90 degrees. And the side opposite the right angle is called hypotenuse. The other two sides are called the legs, or what you can call the adjacent, right? So let's talk about that. So we've classified according to sites now. So um classification according to sides. So we can also classify according to angles. Okay, so I'll run through all of that. So classification according according to angles. Okay. So first of all, before we begin to even talk about the triangles, let's talk about the possible angles we have. We have angle 0 degrees, for instance, and then from angle 0 degrees, we then have um we can have an angle that is between 0 and 90 degrees. Okay. So we have an angle that is between, so any angle between 0 and 90 degrees is called an acute angle. So we have acute angle between 0 and 90 degrees. And between 90, so an angle so this is just zero angle, right? Zero angle. And then we can have An angle between an angle of 90 degrees is called a right angle. Okay, right angle or rectangle. So it's right angle. And between 90 degrees and 180 degrees, we have um what you can call obtuse angle. So it is bigger than 90 but less than 180. So that's an obtuse angle. An angle at 180 degrees can be said to be what you call line angle. So because the sum of angles at a point, I mean the sum of angles on a line is 180 degrees. And then between 180 degrees and 360 degrees, okay, you have what you call reflex angle, reflex angle. Interestingly, 180 degrees and 0 degrees coincide, right? So 180 degrees, I mean 0 degrees is usually seen to be similar to 360 degrees because that's like 0 degrees is point, 360 degrees is a revolution. And angles at a point are said to be okay. Like if you have this point now, that's zero dimensional and that is 0 degrees. In the same way, if you have a complete revolution, that is 360 degrees. So they tend to coincide because if you now have this single point now and you have different angles, you know, projecting from that. So if you add up all these angles now, so this is angle, if this is angle A, B, C, D, E. So A plus B plus C plus D plus E will add up to 100 and will add up to 360 degrees, right? On the other hand, for the 180 degrees angle now, we say that angles on a line. So if you have a straight line and you have angles coming from everywhere. So if you add these three angles together or any number of angles you can have there. So if this is uh PQR, so we say that P plus Q plus R is equal to 180 degrees. So angles on a straight line add up to 180 degrees. Now that we have taken care of all this array of angles now, so we can then have angles based on uh this acute, right, obtuse, and reflex. So so based on angles now, we have these four types of triangles, right? Based on side, we had scaling, isosceles, and equilateral. But based on angles, now we have acute. So let's look at the one after the other. So we have acute angle. So an acute angle is an acute triangle, all right? An acute triangle is a triangle that has an angle that is less than 90 degrees. So imagine, we can always start with a straight line. So you have this angle now. This angle is less than okay. I think one other thing I should have done here is, this is 0 degrees. It's a point. Acute angle is like you have this and this kind of angle. Then you have right angle. So it's like you're opening up this thing. So this is 90 degrees now. And then when you come to obtuse angle, it's like you have this line. So beyond 90 degrees, that extends. And then for line angle, you just have a straight line like this. For reflex angle, you now have so you have the straight line. This is 180 and then you have something beyond 180. But okay, a reflex angle is not even possible, sorry, because a reflex angle now goes back to being like less than 90 degrees. So there's nothing like reflex angle. Yeah. So we only have, there's no reflex angle triangle. So we have acute angle triangle, right angle triangle, obtuse angle triangle, like that. So back here, so we have acute angled triangle, acute angled acute angled triangle. Okay, there's no reflex angle triangle. Acute angled triangle. So it has at least one acute angle here. And this is less than 90. Okay, so if you close this up, this is an acute angled triangle. Then you can also have the next angle we can have is a right angle triangle, like we saw the other on the notes. So right angled or maybe right angle triangle, right angle triangle. So the right angle triangle has an angle of 90 degrees. Okay, this is not looking perfect. I want to try to make it as perfect as possible. Uh, okay, so this is an angle of 90 degrees. So it has, so and that way now you have this, this is angle 90. So the side facing it is called the hypotenuse, and the other sides are called adjacent. But of course, if you know one of the other angles, one of the adjacents will become opposite, and the other one will remain adjacent, right? So like if we have this now, this side becomes opposite, okay? But on the other hand, if we have this adjacent becomes opposite. So we'll talk about that as we move on. So, and then finally, we can have what you call the obtuse angle triangle, obtuse angle triangle. Okay. So here now you have so first of all you have this and then you have this. So this angle is more than 90 degrees but less than 180. So this is an obtuse angled triangle like that. So we can classify angles based on sides and the angles they contain. So we have scaling isosceles equilateral classifying by sides. Then we have uh acute angle, right angle, and obtuse angle triangles, classifying by angle like that. Okay, although what I have here is listing this for ball. I think what I've done there is a more elaborate thing. So let's talk about angle sum in a triangle. Like I think I've dealt with this already. In any triangle, the sum of the three interior angles is 180 degrees. So that's angle A plus angle B plus angle C is 180 degrees. That's what I've demonstrated already. This works for every triangle, whether it is scaling, isosceles, equilateral, right, acute, or obtuse. Okay. Then talking about classifying by sides now. So if you classify angles by sides, a triangle has sides 5 cm, 5 cm, and 8 cm. So because two of the sides are equal, all right, 5 cm and 5 cm, therefore the triangle is said to be isosceles. Then another triangle has sides 3 cm, 4 cm, and 5 cm. All three sides are different. So therefore the triangle is scaling, right? Then we have example two now using the angle sum. So in triangle ABC, A is 50 degrees, B is 65 degrees. Find C. Okay. So all you just need to do is add up everything. Angle A plus angle B plus angle C is 180. 50 degrees plus 65 degrees plus angle C is 180. 50 plus 65 is 115. Angle C is plus 115 degrees plus angle C is 180. So angle C is 180 minus 115. And that's 65 degrees. So angle C is 65 degrees. So angle A is 50, angle B is 65, right? Angle A. So imagine you have a triangle this way, and this is ABC. You can name it anyhow you like. Angle A is 60, and or is it 65 now? Angle A is 50, angle B is 65. A is 50, B is 65. A is 50 degrees, and B is 65 degrees. And then we are looking for this. So like we know angle A plus angle B plus angle C is 180 degrees. So that simply means that it's 180 degrees. So that means angle A is 50 degrees plus angle B, which is 65 degrees, plus angle C, which you are looking for, and that's 180 degrees. So if you add the two together, you have 115 degrees plus angle C equals 180 degrees. So angle C is 180 degrees minus 115 degrees. So angle C is simply 65 degrees, like that. Okay. So use that idea. Then we have example 3 for isosceles triangles, right? So triangle PQR is isosceles with PQ equals PR, and angle Q is 40 degrees. Find angle R and angle P. So since P is equal to PR, the angles opposite them are equal. So angle Q is equal to angle R. So angle R is 40 degrees. Now, using the angle sum, we have angle P plus angle Q plus angle R is 180. So angle P plus 40 is 180. So angle P is 80, which angle P plus 80 is 180. So angle P is 180 minus 80, which is 100 degrees. So angle Q is 40, angle R is 40, angle P is 100 degrees. Well, I mean, that's me just going through that. Let me actually go and do it now. So PQR is isosceles, right? With PQ equals QR. Okay. So let's deal with that on the worksheet and see how that goes. Okay, so we come here now. I want to change this. Oh, okay. All right, let me change this to blue. Blue was there before. So we have that angle. So triangle PQR. So we have that triangle PQR is isosceles with PQ. Line PQ is equal to PR, and angle Q is equal to 40 degrees. Okay, so we now need to find, we're looking for angle R and angle P. Okay, we are looking for this. So we can just draw the triangle. So you have the triangle. You can label anyhow you like PQ R. So we said PQ is equal to PR. So this PQ is equal to PR. And of course, RQ will be different from all of them. And angle Q is 40 degrees. Now, one thing we know already is that for an isosceles it's an isosceles triangle like this, the angle in any triangle at all, the angle facing the the angle facing each side is proportional to that side. So it means that if this side is equal to this side, then the angle facing each of the side will be equal to. So the angle facing this side is this angle, and the angle facing this side is this angle. So, and we know that for an isosceles triangle, for an isosceles triangle, the base angles are equal. And what we mean by base angle is this, that the angles at the feet of those two sides are equal. So it means that angle R and angle Q are the same. So angle Q, which we know already, is equal to angle R, and that'll be 40 degrees. Okay, so if we need those other angles, so I mean we've already found angle R automatically because it's simply equal to angle Q, and then we now need angle P. So to find angle P, so we have that angle P plus angle Q plus angle R is equal to 180 degrees. So angle P now plus angle Q, which is 40 degrees, plus angle R, which is another 40 degrees. That's 180 degrees. So angle P plus 80, 40 plus 40 is 80, equals 180 degrees. So angle P is equal to 180 degrees minus 80 degrees. So angle P is simply 100 degrees. Okay. And with that, now we know that angle P is 100 degrees, angle Q is 40 degrees, and angle R is also 40 degrees, because if we add everything together, you have 180 degrees. So that's how that goes. Then we move on here to the next thing. So next, since we have been introduced to the whole concept of triangles, talking about their classification based on angle, based on side, and all of that. Next thing, we want to solve triangles. How do we solve triangles? So in solving triangles, I want to consider how to solve triangle using Pythagoras theorem, or if you like, Pythagoras rule, sine rule, and cosine rule. So in this section, we learn three important tools for solving triangles, like the Pythagoras theorem for right angles, right triangles, then sine rule for any triangle, cosine rule for any triangle too. Of course, uh, with specific properties, by the way. So first of all, let's go for Pythagoras theorem. So in a right angle triangle with legs A and B and hypotenuse C, C squared is equal to A squared plus B squared. So use this to find the missing side in a right triangle. For instance, a triangle has sides 6 cm and 8 cm. Find the hypotenuse. So we use C squared is A squared plus B squared. That is C squared equals C squared plus 8 squared. That's 36 plus 6 squared equals 100. And C is square root of 100, which is 10 cm. So the hypotenuse is 10 cm. Now, the reason why I just run through this is because, I'll still go to the worksheet to do it, it's really clear like that. So now we are solving triangles. So, and we start with Pythagoras theorem. Okay, Pythagoras theorem. This video, once with this video, you need everything you need to know about triangles, you can get it. So we start with Pythagoras theorem. If you look at the playlist on trigonometry, I think I showed how to prove the Pythagoras theorem there. So in this case, I won't just bother. So first of all, you need to get a right angle triangle out like this, and we know that this side is called the hypotenuse, and the other side are called the adjacent. So let's imagine that this is A, and this is B, and then this is C, right? So the Pythagoras theorem simply tells us that the hypotenuse the square of the hypotenuse is equal to. So now, if you know an angle, hypotenuse is simply equal to the square of the hypotenuse is equal to the square of the first adjacent. Let's say this is adjacent 1 squared plus adjacent 2 squared because now I don't know which is opposite. I need an angle to know which is opposite, but for now we don't really care about that. So the hypotenuse here is actually the longest side, and it is usually the side facing the right angle. So this is the right angle. So the side facing it is the hypotenuse. So the hypotenuse is now c squared, and that is equal to a squared plus b squared. So based on this, now you can easily know that a squared is equal to c squared minus b squared. In the same vein, b squared is equal to c squared minus a squared. So if you now need to find anything, so it means that if I give you, if I tell you that that you have, imagine like apart from getting a right angle triangle like this, you can get from an equilateral triangle, you can easily drop a line to get a right angle triangle. So you can then apply Pythagoras theorem to the two sides. The same thing is applicable to an isosceles triangle where two sides are the same. So if you drop a height like this, it's also you also get the line meeting it at 90 degrees. So you can still operate, you can use the idea of Pythagoras theorem. So the example we had there is, imagine, I mean, it can be in any form. Imagine you have a right angle triangle this way. Okay, I want to try to make it as accurate as possible. Of course, it's not the best way to go, but at least this is something. So imagine that you have this is 6 centimeters, this is um this is 8 centimeters, and we now need to look for x. Okay, we know that x, of course, is the hypotenuse. So we know that 8 squared plus 6 squared is equal to x squared, right? That means that x squared is equal to 64 plus 36, and x squared is equal to 100. That means that x is square root of, normally you should have plus or minus square root of 100, but we are talking about length, so it has to be positive. So we forget the minus side and we have 10 centimeters. So x is 10 centimeters. So imagine again that you have this right angle triangle. You have this right angle triangle, okay? And you have this side to be 7, and this side is 3, and this is y. So how do you look for y? You know from Pythagoras theorem, right? That y squared plus 3 squared is equal to 7 squared, okay? So that's y squared plus 9 equals 49. Okay, so that y squared is equal to 49 minus 40. So that means that y squared is equal to, sorry, for I've jumped the gun. I was already getting ahead of myself. 49 minus 9 is 40. So y is equal to square root of 40. So y is 4 times 10, right? That's square root of 4 times 10. So I brought the 4 out because of it's a perfect square. So y is equal to 2 root 10 units because I didn't specify. If I specify a unit like cm, then it's fine. But here it's 2 root 10 units. So, and you can then use calculator to get 2 root 10 and multiply it by 2, and that'll be fine. So that's the idea of Pythagoras theorem. So you can always use that. I mean, that's a very popular one. In fact, it's one of the oldest discoveries in mathematics, that the square, if you have a right angle triangle, the square of the hypotenuse is equal to the sum of the squares of the two adjacent sides. So now we talk about sine rule, which applies to any triangle, but of course, any triangle with some specific conditions as we're going to see. So for any triangle ABC with sides A, B, and C, opposite angles ABC and opposite angles ABC. So A over sine A is equal to B over sine B is equal to C over sine C. And we use this sine rule when you know two angles and one side. So if you know any two angles and one side, you can use the sine rule. Then another case where you use it is when you know two sides and one angle opposite. You know two sides and one angle opposite one of them, right? So um, so imagine this now. Of course, now I'm still going to. Okay, I think I should explain this now. So it's important to identify when you can use sine rule, right? So when do you use sine rule? Talking about sine rule, okay. So if you have if you have you have a triangle with two known sides, I mean two known angles. So imagine you know this angle and you know this angle. So you can use sine rule for that. Or if you know any two angles, in short, because if you know two angles, you automatically know the third angle. So imagine you know this angle and this angle, you can use sine rule. If you know any two angles, say you know this and this, you can use sine rule. So that's condition one for using sine rule. So once you know any two sides, to any two angles, you automatically know uh the third one. So the second condition is when you know any two sides, I mean any two angles, imagine that you know this angle, and any side facing one of the angles. So maybe you now know this side. I'll just use a stroke. Okay, you know this angle. Okay, let me follow the same pattern. So imagine that uh you know this angle and this angle and any side facing these two known angles. So let's say you know this side, or or maybe it's like this. You know this angle, you know this and this side. Okay. So in that case, you can use sine rule. Another possibility is maybe you know these two angles and either this side or this side. Say, this two, this, and you know this side. So the two known, have a two known angle and a side facing any of the angles. Of course, there are two other possibilities in that regard, right? So now this and this. So and this side, okay? Or this and this side. So two known angles. So here, this one is called is the AAS now. AAS. Here we have angle side or angle side angle. Okay, angle side or angle side angle, or side angle. So those are the conditions under which you use sine rule. And what does the rule simply state? The rule tells us that if you have a triangle A, B, C, and you know any of the two sides, or any of the two angles rather, or two angles with a side facing one of the two known angles, then small, okay, these are the angles now, A, B, and C, capital, and the sides are A facing A, B facing B, and C facing C. So A over sine A is equal to B over sine B is equal to C over sine C, like that. Okay. So in that case now, you can use sine rule for this. So a very good example is this now. So in triangle ABC, you have 40 degrees. Angle A is 40, angle B is 60. So you already know two angles like that. So you can automatically know the third side like that. So side A is now 7 cm. So that's side A is opposite angle A, like we already know. So find side B opposite angle B using the sine rule. So you have A over sine A equals B over sine B. Yeah, yeah, that means 7 over sine 40 degrees equals B over sine 60. So that B is now 7 over sine 60 degrees all over sine 40 degrees. So you can use the calculator to find the numerical value if needed. I mean, this is a general thing. So angle A is 40, angle B is 60, side A is 7. Okay. Angle A 40. So you imagine you have this A, B, C. Angle A is 40 degrees. Angle B is 60 degrees, right? And side A is 7 centimeters or so. Is it 7 centimeters or 7 meters? Whatever that is. 7 cm, yeah? So, um, so what do we do with this now? So in fact, you can solve this triangle completely. First of all, you can find angle C by because you already know that angle A, okay, let me just go step by step to find angle C now. You know that angle A plus angle B plus angle C is equal to 180 degrees. That's sum of angles, sum of angles in a triangle. So, and angle A is 40 degrees, angle B is 60 degrees. Sorry, angle A is 40 degrees, angle B is 60 degrees, and angle C is what you're looking for. That's 180 degrees. Everything added together is 180. So that means angle C is simply 40 plus 60 is 100. So you have 180 degrees minus 100 degrees. So angle C is simply 80 degrees. So that's settled. And since you know that, you can then find, and side A. So you can automatically find you can easily find side B and side C. Okay? So we can say to find side A and side B. So we can use the sine rule now. Using the sine rule, we know the sine rule is A over sine A equals B over sine B equals C over sine C. Okay, so what is A now? We know side A to be 7. Sine A, we know angle A already. Angle A is 40 degrees. Okay, so that's sine 40 degrees equals side B, which we don't know, and we know sine B is 60 degrees. I mean, B is 60 degrees, that's what I mean. And then C is 100. So C we don't know, all over sine 100 degrees. So from here now you can find B and C. So to find B, so to find B specifically, so we just pick out these two. We have 7 over sine 40 degrees equals B over sine 60 degrees. So cross multiply. So you have B sine 40 degrees equals 7 sine 60 degrees. So that means that B alone, which you're looking for, is 7 sine 60 degrees. Divide both sides by sine 40 over sine 40 degrees. Sine 60 is, I think, root 3 over 2, but I mean, you can punch your calculator and you get your B here. So then to find sine C, you just extract, just carry what you know together with what you don't know, and you can find sine C. I mean, you can find C. So you have 7 over sine 40 degrees now is equal to C over sine 100 degrees. That's picking, since the law tells us they are equal, so you can look for C now. So you have C sine 40 degrees equals 7 sine 100 degrees. So that C is 7 sine 100 degrees all over sine 40 degrees. And that's what you have for C. You can punch your calculator to get all of that in decimal and all that. Right. So that's about the sine rule. So you use the sine rule when you know two angles of a triangle, two angles on one side, right? And knowing two angles automatically means you know all the angles. Then the other condition is that you know two angles and a side facing the other one. Okay, I mean, let me give an instance of that before I even go to cosine rule. That's not in the notes, but I think it's important to give it an example of that. Imagine that you have something like this. Uh, you have a triangle ABC, anyhow you like it, or you can even say PQR, anyhow. So you have PQR, and assume that this angle is 70 degrees, and this other angle is 50 degrees. Let's say we have that. So you know those two angles, and then you now know any side facing either of them. So let's say this now is 7.5. Okay. So this is a very good case for sine rule because you have angles P. So you have angle P is 50 degrees. You have angle Q to be 70 degrees. Now angle R, we don't know. So that's what it means to solve a triangle, right? So let's say this is 7.5 meters. Okay, so now we know small p, this is small p now. We know p to be 7.5 meters, and small q, this is small q here. Small q, we don't know. Small r, we don't know. This is small r. So sometimes they can tell you to solve a triangle completely. To solve a triangle completely means to find, a triangle has 6 features, three sides and three angles. So to solve a triangle completely is to use whatever, and mostly you need at least three information about the triangle to solve it completely. So to solve it completely means to find everything that is missing. So angles P and Q are given. Side P is given. So the angle R you need to find. Angle Q and R you need to, yeah, sides Q and R you also need to find. And because the two angles given now, you also have the angle facing one of them. You can use sine rule here. That's how you can use sine rule, right? So what do you do in that case? You have um you have, of course, first of all you can find angle R, right? So okay. I think I misinterpreted the second part. I think it's a side angle, right? You have two sides and an angle that is not included between them. Yeah, this is what I should have done here. Okay. Let me try to revisit this. This is not about angle, sorry. That must have been confusing. So if we look at the rule again, it's a side angle. So it says the second rule, two sides and one angle opposite one of them. Okay, two sides and one angle opposite one of them. So that means we have that's side angle. So you have, maybe you are given this side and this side. Okay, let's say you have this side and this side, and one one angle opposite one of them. Say you have this. Say you have this, or you are given this side and this side, and then you have this, you know, or you have this side, and one angle opposite one of them, like say this, or you have this side, and one angle opposite one of them, like this. Sorry, it's not about angle and side, it's side and angle. So imagine you now have this side, and one angle opposite the one of them, or you have this side, and this angle opposite one of them. So these are the possibilities. So side, and angle opposite one of them. That's the deal, not the other way around. So I think uh so I need to adjust the problem here. So it means you have, say you have this side P, okay, you have side P and side Q, which is, let's say side Q is 9.2 meters, right? So here now, angle Q is 70 degrees, okay? So you need to look for angle angle P. You need to look for angle P. You need to look for angle R. You also need to look for, so you have two sides now. You have side P, which is 7.5 meters, and you have side Q, which is 9.2 meters. So you need to look for side R. So to solve this completely is to find all these three things that are missing. Okay. So I because you have two sides and an angle facing one of them, then you can use sine rule. And sine rule here just says that, so sine rule here would mean you have P over sine P equals Q over sine Q equals R over sine R. Okay. And then you can fix all of that up. So P is 7.5. So 7.5 all over sine P equals Q. What is Q now? Q is 9.2. 9.2 over sine Q. Sine Q, we know, is 70 degrees. Okay. Or let me make it something that can be handled easily. Let me make it 30 degrees. Okay. Let me make it 30 degrees so we can easily handle that. So now I'm making this 30 degrees intentionally for easy handling. Okay. So this is now 30 degrees, and this is R over sine R. So we have R all over sine R. We don't know either of these two, but we can, once we find P, for instance, we can easily get R and R. So from the setup here, you see, you note the two things here, you know, one here. So we can easily combine these two instead of combining with this other one because nothing is known here. So let's combine these two together and we can find angle P. So we have 7.5 all over sine P equals 9.2 all over sine 30 degrees. Okay, so you can cross multiply. You have sine P, or better still, you have 9.2 sine P is equal to 7.5 sine 30 degrees. Okay, so that sine P can now be 7.5. Sine 30 is 0.5 all over 9.2. So when you get that now, P now is going to be arc sine of whatever you get there. So 7.5 times 0.5 all over 9.2. So once you get P now, you can then say angle P plus angle Q plus angle R is equal to 180 degrees. So you can easily find angle R, which you don't know now, by saying 180 degrees minus whatever you get from angle Q is already 30 degrees, minus angle P, which you would have found from here. So using your calculator, you can take care of all of that. Okay. So we have again cosine rule. Okay, I think I won't waste time on this again. So for cosine rule now, you have it in three ways. For any triangle, also, well, given some certain conditions. So for triangle ABC, you can have A squared equals B squared plus C squared minus 2BC cos A. Similarly, B squared is equal to A squared plus C squared minus 2AC cos B. And C squared is the same, can also be A squared plus B squared minus 2AB cos C. So use the cosine rule when you know two sides and the included angle. That's side angle side. So all three sides, SSS, I want to find an angle. For instance, now, when do you use cosine rule? All right, cosine rule. So you use cosine rule If you don't know when to use either of them, just remember, I think it's easy to remember for cosine rule. So any rule that falls outside the conditions for cosine rule, then you just know you need to use sine rule automatically. So for the conditions now, you need two sides like this and the included angle. Okay, maybe you have this side and the angle in between them, like that, and the included angle, or two sides, say this and the included angle. So that's condition one. Condition two is if you have all three sides. So you have all the sides given, okay? So you know you can use cosine rule. And what does the rule say? The rule simply says that if you have a any triangle at all, and this is A, B, C, okay, and this is small a, small b, small c, then so now this one is now split into three. So you have a separate formula for each one. So you have a squared. So a squared plus a squared, right, is equal to a squared is equal to b squared plus c squared minus 2bc cos big A. Okay? And the same goes for the others too. That b squared is equal to a squared plus c squared minus 2ac cos b. And of course, c squared is a squared plus b squared minus 2ab cos c, like that. So you just need to put everything together to get your results. So, so given two sides and included angle, or given three sides. So any rule that does not follow this, you can use sine rule in that case. So I'm just going to follow the example here. So for cosine rule, a triangle has sides B 7 cm, side C 9 cm, and the included angle is angle A 50 degrees. So find side A, that's opposite angle. So using a squared plus find that side A, right? So a squared plus b squared plus c squared. I mean, a squared is equal to b squared plus c squared minus 2bc cos A. So you have a squared equals 7 squared plus 9 squared minus 2 times 7 times 9 cos 50. So you have 49 plus 81 minus 186 cos 50. So A is the square root of 130 minus 126 plus 50. So you can punch calculator for this. So in this case now, so we have the sides B and C. Okay. Okay, well, I can even use the same one I've been using. So we have sides B and C in this situation now. So for side B and C, um, I think one is 5 cm. Okay, we have for side B. Okay, side B is now 7 cm. Side B is 7 cm and side C is 9 cm. So you have these two sides. And then you have angle A. Angle A now is 50 degrees. So you see, you have these two sides and the angle in between. So you can easily get A squared. You can get A from here by saying A squared is equal to B squared, that's 7 squared plus 9 squared. This is 9 plus 9 squared. Okay, plus 9 squared minus 2 2bc, that's 279 cos A, that's cos 50 degrees, and then you can solve this and get your result out of that. Okay, so those are two conditions right there. Yeah, having done that, then we can move on to the idea of perimeter. Now, because sometimes if you need to find the perimeter of a triangle, of course, it means you need to know all the sides. That's why it is important to know how to solve a triangle in the first place. So perimeter of triangles and triangle inequality. We now focus on perimeter of triangles. The triangle inequality, when three sides can form a triangle. Not all possible values, not every three possible values can form a triangle. That's why this triangle inequality is important. So first of all, we start with the perimeter of a triangle. So the perimeter of a triangle is the sum of its three sides. So if the sides are A, B, and C, so perimeter is A plus B plus C. That's a very simple idea that, the reason why I had to go through knowing how to solve a triangle is because you may need to find the perimeter of a triangle and you don't know all the sides, right? So if you have, let's say this is side A, B, and C. So perimeter is simply A plus B plus C. So imagine now that you now have a triangle. You're only given one side, and with maybe you're given one side and two angles or something like that. You need to use either sine or cosine rule, anyone that works, to find all the sides. Then you can now add the sides together. that was the usefulness of knowing how to solve triangles. So perimeter is just straightforward. So a triangle has sides 4 cm, 5 cm, and 6 cm. The perimeter is simply 4 plus 5 plus 6, which is 15 cm. So the perimeter is simply 15 cm. So example 8, we can talk about perimeter from coordinate system, right? So on a coordinate grid, consider, I mean, I think I talked about this a lot under coordinate geometry. So you want to check out that whole playlist. So on a coordinate grid, consider triangle with vertices. So A 0, 0, B 3, 0, and C 3, 4. So find the perimeter. So length, you have AB from 0, 0 to 3, 0. The distance is 3. Then from BC, we know how to find distance, right? So from 3, 0 to 3, 4, the distance is 4. From for AC 0, 0 to 3, 4, we can use Pythagoras theorem now to find AC, which is square root of 3 squared plus 4 squared, and that's simply 5 at the end of the day. So at the end of the day, we know 3, 4, 5. So 3 plus 4 plus 5, that's 12. So the perimeter in this case is 12 units. So now, this is a very important idea now. So, triangle inequality intuition. This is really important. I think in one of the previous videos, I just picked some three values, and I wasn't sure if they were going to make a triangle because not uh, all the three numbers you pick can form a triangle. For three lengths to form a triangle, the sum of any two sides must be greater than the third side. So, for sides A, B, and C, for instance, now A plus B must be greater than C. B plus C must be greater than A, and C plus A must be greater than B. So if any of these fail, the three lengths cannot form a triangle. So the intuition is think of the sides as sticks. If two sticks together are too short, they cannot reach to form a triangle. So how do I know that? Okay, let's even try 3, 4, 5. So can 3, 4, 5 form a triangle? Okay, so to check, can three can okay, let's say can sticks of lengths can sticks of length 3 cm, 4 cm, 5 cm form a triangle? Okay. So how do you know if they can form a triangle? Add any two, it must be bigger than the other side. So 3 plus 4 is 7. It is greater than 5. Nice. Then 3 plus 5 is 8. It is greater than 4. Nice. Then lastly, 4 plus 5 is equal to 9 and it's greater than 3. Correct. So yes, yes, they can form a triangle. They can form a triangle. Okay. So now I'm going to pick any three random numbers and see if the same is true. So let me pick 2, 5, and 2, 5, and say 2, 5, and 3, right? So 2 plus, okay, let me pick 2, 5, and 4. Yep. Yeah, let me just pick it. Or let me pick 2, 5, and 2, 5, and 8. Yeah, 2, 5, and 8. So 2 plus 5 is equal to 7, and that is less than 8, right? Then we have 2 plus 8, and that is equal to 10. That is greater than, what's the third side now? That's greater than 5 for sure. Then you have 5 plus 8, that is equal to 13, and it is greater than 2. So these two are bigger, but this makes it not possible. So 2, 5, you cannot have a triangle that have sides 2, 5, and 8. It's not possible. So as far as triangle inequality is concerned, that won't work. Okay. So from today, I mean, I've learned about triangles all my life, but I never came across this idea. So can these sides form a triangle? Okay, 3, 4, and 8, for instance. 3 plus 4 is 7, and 7 is not greater than 8. 7 is less than 8. So since 7 is once one of the rules break down, then you just know these sides cannot form a triangle easily. Then example 9b, 5, 7, and 9. So 5 plus 7 is 12, greater than 9, correct. 5 plus 9 is 14, greater than 7, correct. 7 plus 9 is 16, it's greater than 5, correct. So all three conditions are satisfied. So these sides 5, 7, and 9 can form a triangle, but side 3, 4, and 8 cannot. Okay. So if you try to, no matter how hard you try to draw any triangle with this kind of size, it won't ever work. Right. So let's talk about areas of a triangle. You know, we are talking about length, areas, and volumes. So for a triangle is a plane shape. So we can easily find its perimeter and its area, but we won't be able to find the volume of a triangle because it is a plane shape. So the area of a triangle is usually given by half times base times height. So the base is any side you choose. So the height or altitude is the perpendicular distance from the opposite vertex to the line containing that base. So I mean, I've given an example of height the other time. Like, if you have if you have a triangle like this, you can always draw a line from here to meet perpendicularly here. So this now becomes height, and here is what you consider as the base, right? So, and the area of the triangle in this case, area of triangle is now half times the base times the height, like that. Okay. So any triangle can be reduced to this idea. So let's talk about the positions of the height can now vary. For an acute triangle, all angles are less than 90 degrees. So the height from any vertex falls inside the triangle. So for an acute angle, right? That's an acute angle triangle. So, you have this, and this is an acute angle right here. If you drop this, so the height will always fall inside here. Okay. So this is the height now, and this will automatically be the base. The line down there will be the base. And then, so the height can take different shapes. For a right angle triangle, one angle is 90. So if you choose one leg as the base, the other leg is automatically the height very easily. Okay. So for a right angle now, the height is easy, is already there. So imagine you have a right angle triangle. Okay, so this is the height. Okay, if this is 90 degrees, this is the height. Automatically, this will be the base. Or if you choose this one, if you choose this as the height, okay, if you choose this as the height, this is automatically the base. Anyhow you choose it is fine. Okay, so the height can also come like that. So the other part now, for obtuse angle, one angle is greater than 90 degrees. So the height from the obtuse angle vertex to the opposite side lands outside the triangle. So you extend the baseline. Okay. So for an obtuse angle triangle now, let me try to see how that goes. So imagine you have this and this comes like this. So if you want to drop a height, um, mm, well, I mean, if you draw a line like this, you can easily get the height. Or, if you try to drop another height, you may need to do some kind of extensions for that, like it's been said there. Okay. The height from the obtuse angle vertex. Okay. So if you are started from this is the obtuse angle vertex. So the height to the opposite side lands outside the triangle, you extend the base. So that means there's something I didn't draw well there, but it's okay. So let's talk about right triangle as half of a rectangle. Okay. Um, so a right angle triangle can be seen as half of a rectangle. So place the right angle at a corner of a rectangle. The legs of the right angle becomes the side of the rectangle. So the area of the triangle is base times height in that case. So the area of the right angle is now exactly half of that. That's area of triangle. So area of triangle, anyhow you look at it, the area of triangle always become half times base times height. In the next video, I think we'll be talking about squares and rectangles. So, but of course, we already know what a rectangle looks like, right? So imagine that you have this rectangle, and then so if you take this as 90 degrees, and you of course, all the angle in a rectangle is 90 degrees. So if you draw this line now, this is like, this is length and this is breadth. So area of a rectangle normally, area of rectangle is equal to length, or okay, since we are talking about base and height now. So this is base and this is height. So that is basically uh base times height for a rectangle. But since now you have divided it into two. So area, okay, let me even number it. This is A, B, C, D. So area of triangle rectangle A, B, C, D is equal to base times height, you know. So now area of triangle, any of the two triangles you pick, let's even say triangle ACD is equal to half times base times height. So anyhow you look at it, the half times base times height still works anytime, any day. Okay, so you can deal with a simple area like what we have here now. We can deal with a very simple area like this. So a triangle has base 10 cm and height 6 cm. Okay, so the area, of course, we know is half times base times height. So the base is 10 cm, the height is 6 cm. So that's 30 centimeters squared. Example 11, you have right angle area from leg. So a right angle has 3 meter and 4 meter. has legs. So that is the adjacent at 3 meters and 4 meters. So we can pick base to be 3 and height to be 4. You can switch it anyhow you do it. You have half times 3 times 4, half times 4 times 3, anyhow, whatever you pick as base or height. So at the end of the day, you have 6 meters squared as your area. And then example 12, you have obtuse triangle. You have the height outside, right? So a triangle has base 12 cm. The altitude from the opposite vertex to the extended base is 5 cm. So we still use the same formula, half times base 12 times 5, that's 30 cm squared. So even though the height lands outside the triangle, the area formula still works. So half base times height does not fail as far as triangles are concerned. So we now focus on two special types of triangles like right triangles and equilateral triangles. So for right triangle now, we have area from the legs. So if A and B are the legs, the sides forming the right angle, then the area is half A times B. Okay? I mean, if we have, you have a right angle triangle like this. So, and the legs are just A and B. So this one is automatically base, one is automatically height. So the area will just be half times base B times height A. So that's half AB. So it's still the same thing we are talking about here. Okay. So, so for right angle with Pythagorean triple, a right angle has legs 5 cm and 12 cm. So the area is half times 5 times 12, and that is 30 centimeters squared. The hypotenuse for practice now. So if you need to find the hypotenuse, of course, we already did that using Pythagoras theorem the other time. That would be c squared is 5 squared plus 12 squared. That's 25 plus 169. So c is square root of 169, which is 13 cm. So the hypotenuse is 13 cm. The area is 30 centimeters squared. So, but of course, all you need are the legs to find the area. So equilateral triangle, height and area now. So in an equilateral triangle with side length S, all sides are S, all angles are 60 degrees. So if you drop a height from one vertex to the opposite side, this side splits the triangle into two right angles. Each right angle is 30 minus 60 minus 90 triangle. In that right angle, the hypotenuse is S. The shorter length, that's half of the base, is S over 2. So the height H is longer leg, which is H, that's root 3 over 2S. Well, I mean, this is what we're talking about here. The focus is now on an equilateral triangle. So you have an equilateral triangle. Okay, this is not looking quite like an equilateral triangle, but let me try. It's maybe hard to get one. Yeah, this is it now. So you have all the sides to be S. So if you drop, I mean, this is not perfect, but it's okay. So if you drop this now, this is a right angle triangle, and then you see this one side now is now each of this side now, but this height we just divide into S over 2 each, S over 2, and we need the area, right? Area is, of course, we also know that this is 60 degrees. This is 60 degrees. After dividing this, each of this will be 30 degrees, and this is 30 degrees. So we need to know this S over 2, what exactly this S over 2 is. So, uh, so we need, or rather, we need this height. Now we need this height. Yeah, it is this height we need. So, we need the base, of course. So we have times half times base times height. Okay. So the base is S done. So half times S. We now need this height now. So how do we find this height? Okay, or let me say small h here. So we need this small h. So if you draw this properly, so this is height. This is S over 2. This is S, and this is 30 degrees, and this is 60. So we have everything we need. This is right angle. So we need H now. So this is opposite over hypotenuse. That's cosine. So here we know that cosine of 60 degrees is equal to okay, yeah. We need the height, right? So adjacent over hypotenuse. Yeah, opposite over hypotenuse, that's cos 60 here. So it's sine 60. Sine 60 degrees that's opposite. So opposite, that's H over hypotenuse S. So and we need H now. So sine 60 degrees is root 3 over 2. I mean, I did that much under the trigonometry playlist. So what we need is H, right? So we have okay, this is H over S, not 2. H over S. So if you cross multiply, we have 2H is root 3S. So that H is now root 3 over 2S. That's the height now. So we can say that area of the triangle is half times base s times the height root 3 over 2s. Okay. Hope that aligns. Root 3 over 2s. Yeah, the height alone is root 3 over 2s. So the whole area, hypotenuse is s, shorter length is the s over 2. So height is the longer root 3 over 2s. So that's what we have found here. So we found the height here. So the height is root 3 over 2s. So the area is um half times s times root 3 over 2. That's more like root 3 over 4s squared. That'll be the area of any equilateral triangle, root 3 over 4s, like that. So, but of course, it's not that deep most times. You can easily just find the height if you have the numbers and then you move on like that. Okay. So, okay, yeah, this is the root 3 over 4s squared I got there. So, imagine area of an equilateral triangle with side s. Area is half times base times height. That's half times s. The height is root 3 over 2s that we found. So the area is root 3 over 4 s squared. For an equilateral triangle, root 3 over 4 s squared is always the answer. So let's check this out now. So we have equilateral triangle. We want to find the area. Okay. Um, so there we have an equilateral triangular side 8 cm. That's all you need. So the area is simply root 3 over 4 times 8 squared. So that's root 3 over 4 times 64. 4 in 64 is uh 16. So that's 16 root 3 centimeters squared. So you can punch your calculator. Approximate value for root 3 is 1.732. 16 times 1.732 is approximately 27.7. So the area is approximately 27.7 cm squared. So we can also talk about triangles on a coordinate grid. So we often meet triangles whose vertices have coordinates like x, y on a grid. So we can find side lengths using coordinate differences, area using base and height, especially when the triangle aligns with the axis. Then using base and height aligned with axis. So if a triangle has a base line on the x-axis, horizontal on the y-axis, vertical, and the third vertex is directly up above or beside the base, then it is easy to see the base and height. So steps: choose a side as the base, preferably horizontal or vertical. Find the height at the perpendicular distance from the opposite vertex to that base. Then use half base times height. So half base times height always works. So in example 15 now, we have that kind of idea. So right triangle on the axis. So A is 0, 0, B is 6, 0, C is 0, 4. So base AB will just be length 6. Height, the point C now from 0, 4 is 4 units above the x-axis. So the height from C to AB is also 4. So in that case, the area is just half times base times height. And we have half times 6, 3, 3 times 4 is 12. So the area is 12 square units. I mean, I'm just jumping over that because I've done a lot of work on this under uh, coordinate geometry. So if you have vertices 1, 1, 5, 1, 3, 4. So draw the bounding rectangle with corners. So you have 1, 1, 5, 1, 5, 4, and 1, 4. Okay. So you have the width to be 5 minus 1, which is 4. The height is 4 minus 1, which is 3. So area of the rectangle is 4 times 3, 12. So half of that is going to give the area of the triangle, because we also saw that a right angle, a rectangle can be divided into two right angle triangles. So step 2, notice that the triangle ABC forms exactly half of this rectangle. The diagonal from 1 to 1 to 5, 4 can form the triangle. So the area of the triangle is half times whatever the area of the rectangle is, and that is simply 6 square units. So another thing we can do is we can decompose shapes into triangles. So complex shapes can often be broken into simpler pieces. So a powerful idea is triangulation, cutting shapes into triangles. For instance, you can triangulate a polygon. So any simple polygon, no crossing sides with end sides, can be split into n minus 2 triangles by drawing diagonals from one vertex. For example, a quadrilateral that has 4 sides can be split into 4 minus 2 triangles. Just like what we saw about a square or a rectangle, you can just use a diagonal line to divide it into two triangles. Then you have a pentagon, 5 sides can be split into 5 minus 2 triangles. Then find the area of each triangle, add them to get the total area of the polygon. So if you want to find the area of a polygon, that's one nice way to go. And we know the smallest polygon is a triangle, and we can divide that further. Well, we can divide two equilateral triangles into two right angle triangles, so we can do whatever we have to do. But imagine a rectangle, uh, imagine you have a rectangle like we did before, so you can always divide this into two triangles. Then now let's talk about a pentagon. One, two, three, four. So by drawing a line from here to here, from here to here, you have that divided into three triangles. So n is equal to 5. Number of triangles is equal to 5 minus 2, that's 3. So here, n is equal to 4. Number of triangles is equal to 4 minus 2, which is 2. 1, 2, like this. So if you have a hexagon, you see hexagon 1, 2, 3, 4, 5. Okay. 4, 5, 6. Okay. So if you draw a line, 1, 2, 3. So you see you have 1, 2, 3, 4 triangles there. So when the number of sides is 6, the number of triangles will be equal to 6 minus 2, that's 4. Like that. That's what that side is telling us. So you can triangulate polygons like this. So if you are looking for the area of this polygon, just get into the 3 into the number of polygon of triangles and find the area of each and add things up. Okay. So, example 17 now, quadrilateral from two triangles. So, quadrilateral ABCD is divided by diagonal AC into triangles ABC and ACD, like the kind of thing we saw before. So, area of triangle ABC is 18 centimeters squared. Area of triangle ACD is 24 centimeters squared. So, total area of quadrilateral is just 18 plus 24, which is 42 centimeters squared. Then, in example 18, you have an L-shaped polygon. All right. So, imagine an L-shaped figure constructed from a big rectangle minus a small square, right? So the big rectangle is 6 by 4. The small square removed is 2 by 2. Okay, imagine this now. We have a rectangle, 6 by 4. So in fact, let me use this grid. 3, 4, 5, 6. Then by 4, 1, 2, 3, 4. So this is a rectangle, okay, 6 by 4. So this is 6 centimeters and this is 4 centimeters. Okay. Now we want it to be an L-shaped stuff. Um, and then a square is removed, a 2 by 2 square is removed. So let's imagine this is a 2 by 2 square right here. Okay. So imagine we have we have something like this now. Okay, so this is we have a and this place is 2 by 2. This is 2 centimeters right here. So the question is, if you need that area, so the area of the big rectangle is 6 by 6 times 4, that's 24. Area of small square is 2 times 2, 4. So area of L shape is 20. Okay, so we can also split the L shape into rectangles and then split up. So this shows how breaking into triangles can help find the area of the complex shape. So in this case now, we can just say 6 times 4, 24. We can have 6. So area of this shape now, okay, let me keep going. So the area of this shape can just simply be 4 times 6 minus 2 times 2 because, this one has been cut off. So that is 24 minus 4, which is 20 centimeters squared. Another thing we can do is to say, just take it the way it is. We have, this is 1, 2, 3, 4, right? And this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yes. And this is 2 has been cut off. So this is up to this place. We have this now. So all we just need to do, this is 6 cm and this is 4 cm. So if you draw this line now, you see this is of course the whole of the we already know this is 2 centimeters. So this is 2 cm, this is 2 cm. Okay. And now if this is another 2 cm right here. So it means this one is remaining 4 cm. So this is 4 cm. Okay, well, let's do it this way. Let's have this is the original thing, right? So if you want to solve this easily, so you already know this is 2 cm, automatically this is 4 cm right here. Thankfully, this is also 4 cm. Okay, so yeah, this is 4 cm. So 4 times 4. So the area here, you just know that the area here is 4 times 4, 16 cm, and the area here is 2 times 2, 4 cm. So total area will just be area. You have two squares now. So area of big square plus area of small square, that's 16 plus 4 cm. So which gives the same 20 cm like what we have up here. That's 20 cm squared rather. 20 cm squared. This squared, sorry. Yeah. So I mean you have that kind of thing. It's very possible to break things down like that. So finally we have practice because this has been a very long video, but I think it's fine. So once anything about triangle, just get here, you get it sorted out. Okay, so let's look at the questions. I think I won't even bother solving because we've talked about all of these things in depth. So you have all these questions here. First of all, questions 1 to 5. Uh, So with this, I come to the end of this video. Let me know how helpful this is for you. Try your hands on these questions. You'll find them very interesting. We've done everything that needs to be done for you to be able to solve these questions. Let me know how helpful this is. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I thank you very, very much for doing that. If you have not subscribed, of course, what are you waiting for? Go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, of course, you can become a member of the channel also by clicking on join. Okay. And that can give you some special privileges. Um, Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.